Well, hello, my Theosophical Society buddies. This is Jeff Curtis coming to you from the Sierra Foothills again, and oh, don't need that. I am happy to be with you. I guess it's been a little over a couple months since our last such session as this, and what I'm going to do tonight is offer a couple, just some interesting science news that every once in a while I do that as a little bit of a community service. And there's two items have popped onto my screen that I think are worth knowing about, kind of a public service announcement. And then we're going to spend a little while extending some of the technical aspects of artificial intelligence and large language models, how they operate in order to create this very useful new tool that we call artificial intelligence. And if you haven't ever played with it yet, I would encourage you to do so because it's so interesting. So back to that later. Then I'm going to move into opening the discussion about what are quantum computers? How do they work? What's different about quantum computation than standard, what we would call classical computation, which current AI, large language models, they all are operating by virtue of classical computer hardware and so-called bits, ones and zeros that get manipulated. But there's a new thing coming up fast that is going to change the entire landscape. And the way things seem to be accelerating, and it'll probably do that sooner than you might guess. So that's where we're going to go tonight. Before that, I wanted to mention one bit of Theosophical Society news and finery. Those of you who have been associated with the San Francisco Lodge of the Theosophical Society, what you'll know is that for many, many years now, since the time even of Joe Miller, there's been a special practice that takes place during the traditional Christian period of Lent, which we are in right now. And this involved people getting together at ridiculous hours in the morning and then again in the afternoon and alternating back and forth between a small group readings of two sort of crucial and beautiful and special to us Buddhist sutras. One of them is called the Tibetan Book of Great Liberation, which is a long sort of meditative immersion in a particular translation of this book, the Tibetan Book of Great Liberation, that was performed by Evans Wentz back a long time ago and given in manuscript form to Joe Miller. Who sort of immediately fell in love with it. And if you've never attended one of those sessions, you've missed out on something interesting, something kind of shamanic and magical and deep. But right now, during Lent, you can hear these sutras read aloud by either Richard Power or Mary, and we're sort of alternating back and forth. So go to the San Francisco Theosophical Facebook page, and you will find the necessary information in order to know when those are. And you'll be able to obtain for yourself get on the list to get a Zoom link that will allow you to come in. They start at 6 o'clock on weeknights. And some nights it's the Tibetan Book of Great Liberation. Some nights it's the Sutra of Weining, which has some interesting parallels and overlaps and then differences with the Great Liberation. And I would encourage you to try it out. It's really quite something. It's a real gift being offered to us by Richard and Mary, who are night after night performing this service for whoever wants to show up and be part of it. I wanted to mention also that in this particular month, is it this month? Let's see. I take that back. This is in fall of 2023. This is an older issue I had laying around of the Quest magazine from the TS. There is a beautiful, about 6-page long article about the Tibetan Book of the Dead and the liberation through hearing and studies upon the peaceful and wrathful deities. The Tibetan Book of Great Liberation is a little different than the Tibetan Book of the Dead, but there are common themes and ideas and word usages, and they resonate back and forth. This particular article is written by Anatti Savinainen and Tomi Talmunen, and it's very scholarly and interesting and deep. It does a nice job of showing parallels between theosophical concepts and ideas and the ancient Tibetan Buddhist ideas. So if you happen to have this magazine around and you've still got your fall 2023 issue of it, I would recommend give it a look. You might find it a nice complement to the readings that are taking place at the lodge now. Okay, on to a couple of interesting bits of scientific news that I've obtained lately, and I'm going to put them out there to you as public service announcements that don't have exact recommendations attached, but I would say learn more about these things. Two kind of interesting and maybe important things to learn about and keep track of. One is a raft of recent data which has come in regarding usage of the supplement vitamin D. Vitamin D is both a vitamin and a hormone, and it has very important health effects in the body. And any of you out there who are into supplement land and you pay attention to what kind of dietary supplements and vitamins are healthy to take are going to want to hear this. I can remember myself attending a very detailed, erudite, sophisticated lecture by a medical doctor. It's like 15 years ago. Great presentation, sort of earlier in the days of the vitamin D is good for everybody and we should all supplement with it phase of thinking. And he had study after study. Now, most of them were done on relatively small groups of participants. And this is an important point in terms of what scientific studies to pay attention to and base big decisions on. Well, early in the flush of awareness on something, you will oftentimes find relatively small participant number or so-called underpowered studies driving people's speculations and hypotheses, and then eventually recommendations that come out. And I remember this particular doctor, he was just so enthusiastic about vitamin D. He found thing after thing in the body that improved upon taking it. And by the end, he just wanted to leave the lecture hall and go gobble the stuff down. And many people kind of have over the last 20 years or so. Let's put a question mark on that based on some new data that has come out. There may be reason to think that more than about 2,000 international units of vitamin D per day isn't the greatest thing for you. And there are a lot of people out there now that are supplementing with 10,000, 20,000. Now, we know there is some toxicity that gets bumped into when you get up into the 20 and 30,000 IU range of vitamin D supplementation. It begins to mess with your blood calcium levels. And that's a big deal. Your body works pretty hard to maintain blood calcium levels in a fairly narrow window. And that's for all kinds of reasons of nerve function and bone health, bone density, and it's how your body is handling lipids. It's a large lot of things. The calcium needs to be in the right window. We know that if you really overdo it and mega dose on vitamin D, it can knock that out of whack. But now data are suggesting that maybe even much more than 2,000 international units a day can have questionable effects on people. So I would encourage you to take this bit of knowledge as a preliminary but maybe important thing and go do some of research of your own. Go to the interwebs, type it in, and start reading recent, large participant numbers, studies in vitamin D, and then arrive at your own conclusion. I bring it up only because I know many people who are taking what is way more than 2,000 international units a day, assuming that they're doing themselves a big favor. So there's a question mark on that now. That's thing number one. Thing number two, and possibly even more important, actually, is some recent data coming out, and this has been around for a little while in beginning forms. I've heard some things about it, but there's another raft of studies out now. Typically, relatively small sample numbers. So you're going to see the first few years of studies on this topic will not involve thousands of people or organisms in the study, but they can nonetheless be suggestive and something you want to pay attention to. So studies coming out now are showing that we may have kind of a big problem on our hands with microplastics. And you may have heard some things about this. It first started popping up, at least in my awareness, 2-3 years ago, because they were finding these microplastics, which are just, you put plastic in the environment and it sticks around a long time, and it actually erodes into smaller pieces long before it degrades chemically, because depending on the type of plastic and where it is, the rates of actual chemical degradation can be very slow. Whereas erosion through them rubbing on each other or rubbing on sand or dirt or what have you, in order to break into ever finer and finer particles, that can happen with plastics way before chemical disappearance happens. They began seeing burdensome amounts and surprising amounts of microplastics contaminating the cells and organs of marine animals, so fish, crustaceans, and those probably were large N number studies, because it's pretty easy to collect a lot of fish and analyze them to see what their microplastic concentrations are and where the microplastic particles segregate. Here's the part, the punchline. There's a large distribution of particle sizes. So as something like a piece of microplastic is breaking down, there will be a certain number of particles that are in the micron size range. So that's like a millionth of a meter. You can see stuff that's a millionth of a meter. That's a typical width of a shaft of human hair. You can see human hairs easily enough. So particles that are in that size range are not such a problem when they get in your body, because they're not going to get through your skin real easy. Even if you were to ingest those, they probably would not make it through the gut barrier. The lining of your intestinal tract is generally not going to be that permeable to micron and upsize stuff. But there's a certain tail of this particle size distribution that goes down into the nanometer scale. And that's getting down into the size of viruses. And when particles get down to a few tens or hundreds of nanometers, it's a different ball game. So that's a thousandth of a micrometer and less. And they can permeate your tissues, and it looks like they have been, according to recent data coming out. I read one study this morning that was got my attention, which they looked at, they autopsied the brains of, I think it was a total of only 30 or 40 individuals, in order to see how much microplastics were in there. And they found very significant amounts of microplastics in people's brains. And they actually segregated these brains into normal versus abnormal, or brains of people who were exhibiting signs of dementia. And this is just correlation at this point. This is not causation. But they found very significantly more micro or nanoplastic particles building up in brain tissue and segregating amongst the different types of tissues in the brain a little bit in the folks who were having cognitive problems towards the end of their life. Like I said, correlation is not the same as causation. This is not to say really that the nanoplastic particles were driving dementia or dysfunction, but one certainly has to wonder. And in some of these folks' brains, they were finding up to 7 grams of these plastic particles. Okay, that's a lot. That's a shocking amount. 7 grams is, that's like a little bottle full of stuff. A typical plastic spoon you might take to the picnic is about 7 grams of plastic. And so I think we're going to be hearing a lot more about this. And I would suggest that you pay some attention to it, not to get super scared, but pay attention, because there's going to be guidelines, recommendations, revelations. We're going to be learning about, which processed foods are having the most nanoplastics in them. We're going to be learning about best practices to avoid ingesting and or inhaling these things, because they are kind of ubiquitous in the environment. So something to watch. One place, turns out, where people are accidentally dosing themselves with big amounts of these particles is with tea bags. Now, this problem is recognized. The major tea maker brands have kind of figured this out. They're already re-engineering the way they make tea bags so that you're not dosing yourself with a bunch of nanoplastics every time you dissolve tea from a bag into water. Like Bigelow is, I think, already come around. You can look this up very easily, and you can find out which companies are hip to this and have changed the way they're making tea bags. For now, if you have a whole bunch of tea that you've bought, and I mean, like I do, I have tea that sits around for years before I get to it, it's maybe a really good idea to just open those bags with some scissors and pour that tea into, I'm going to go get something. I forgot to bring it over here. I'll be right back. This is an example of a tea canister. You can't quite see it here, but those are little teeny tiny holes. It's a metal canister. Well, maybe you can see it. You can buy these made out of wire mesh as well, and you can cut a tea bag open, pour the stuff in here, and then use this, and you won't be potentially exposing yourself. The reason it shows up in the tea bags is that they use polypropylene, polyethylene, other different kinds of fibers in the bag. So sometimes you'll look at this bag and you'll think, well, that's paper, but it's not really paper. It's a mixture of perhaps cellulose fibers and plastic fibers. And when you're putting those in super hot water and letting them do their diffusion thing, that's when they are releasing billions of these little tiny nanoparticles that you probably don't want in your brain. So, to note. All right, on to the more fun topics that I wanted to get to and talk a little bit about today and open this discussion. In preparing for this, I spent a while brushing up what I thought I knew about quantum computers. I first heard a great talk about quantum computation at one of the events in Arizona that I go to sometimes on the science of consciousness. There's this, every couple of years they have these beautiful large globally attended conferences they used to be called Toward a Science of Consciousness. Now they've changed the name to The Science of Consciousness. Beautifully multidisciplinary. A lot of people from all different walks of science show up there and argue with each other about what consciousness is and how it happens. Is it caused by the brain, or is the brain just sort of picking it up and transmitting it like a TV picks up a show? Certainly the brain has something to do with it, because if you mess with the brain, consciousness for sure changes. Wonderful conferences. Well, the guy who orchestrates and runs those conferences is a fellow named Stuart Hameroff, and he keeps his finger on the pulse. He really knows. So he had a fellow that I got to know a little bit at a conference. This was actually in 1999 in Flagstaff, Arizona. His name was Quentin something, maybe Quentin Torchet. Anyway, gave a great talk and opened my mind to the fact that quantum bits, qubits, quantum objects are capable of interacting in a way that allows for vastly expanded information processing than simple bits or classical bits. So that got me paying attention to it and sensitized me ever since. Just in the last week or so, I've cycled back around to this, and I've just been blown away to see how many groups are working very hard on quantum computation as the next big thing in our technological progress into the future. Many embodiments in different kinds of approaches to quantum computation physically, using different kinds of quantum objects, but they all have these unusual and special properties to them having to do with superposition and entanglement, which are things I've talked about here in these large talks enough times that if you want to brush up on those, I would encourage you to go back and look at talks stretching back for years, and some of which are available on the Lodge's YouTube site, especially my talks from the last 2 or 3 years. And you could pick some of those and you'd get my kind of informal and, fumbly figures type approach to giving the gist of these issues. But of course, there are many, big production, pro-level introductions to quantum objects and what's weird about them and how they work, how they can hold and process information by superposition and by entanglement. There's years of YouTube viewing pleasure out there already on that. Let me back up for a second and mention classical computers, the ones in our laptops. They work off of bits, and you've probably heard this said before. Bits of information just mean pieces of information, and they are held in a binary fashion by flows of current in little transistors. So a transistor is an incredibly ingenious device that we started figuring out how to make and deal with in the 50s. It wasn't long before we learned how to print transistors in high density onto silicon wafers and be able to make circuits of these little switches. Now, these classic bits, they're either on or off. And the on or off, or you could say right or left, these are just two categorizations of the state of the bit. In the ones that in our computers, it tends to be a transistor that will either have a certain finite amount of current flowing through it or a very small amount of current flowing through it that we can effectively call zero. And so the states will be 1 or 0, and you may have seen representations of numbers in binary code. You can take any 10-digit, any number written in decimals, our base 10 unit of number writing, and you can turn it into binary code, which is just a sequence of ones and zeros that, once you learn how to read it, very straightforwardly translates between base 10 and base 2 number systems. Well, they're great. They are so, once you learn how to make what are called logic gates that will add the information in this bit to the information in that bit, or subtract, essentially numbers. What the computer is doing at high speed is that it's adding, subtracting, multiplying, and dividing numbers expressed in these bits in order to go on to the next step of the program. And we don't tend to know this unless we study computer science, but there's a bunch of layers of organization between what's going on with the transistors on a chip and the code that we're using. Finally culminates in English now, and you're able to type in English, and an AI can go out for you and write the machine code that it takes in order to talk to the quantum bits, not quantum, classical bits on a wafer of silicon and execute programs. And it's not magical, but it seems magical. Well, they have their limitations. So these classical bits, they'll maintain their identity for as long as we leave the power of the computer on. Now, there are permanent ways of building bit states into magnetic memory, and there's that, slow storage. But in an active computing computer core, say CPU, central processing unit, most of the memory in there is fleeting. It's turned on a certain state, held there by all the power flowing through the device until you turn the power off, and then your program stops. They can be added, subtracted, multiplied. I'm making that sound easy, just to give you a glimpse of how not easy it is. One sort of interesting little factoid I came up with as I was cruising around today is that in order to multiply some number, whatever it is, by 3, using our current technology in the silicon wafers and the CPUs in our computers, it requires thousands of these little transistors that are operating in comparison and contrast mode. So it takes many logic gates comparing transistor states in various trees, logic trees, and in sequence in order to do something as simple as multiply by 3. Now, it turns out multiplying by 3 is harder than multiplying by most numbers for reasons I wasn't able to figure out. They just made a note of that. They were bringing that one up because multiplication by 3 requires a different level of finesse in the electrical engineering that's taking place in the CPU. But thousands to do a simple step, all right? That's a lot of power. That's a lot of steps. It seems like kind of overload, but there are a lot of really smart people working really hard, optimizing the algorithms and quantum logic gate sequences that do these things for us in our laptops. That you can bet it's being done pretty well. All right, those bits are independent of each other. They can be compared, they can be multiplied, but they're non-interacting otherwise. They're isolated, and they only have 2 states. what about quantum objects? We've spent quite a while in here over the years discussing the properties of quantum objects and some of the surprising things they do. We've talked about superposition, the fact that quantum objects don't exist merely in an up or a down state. They can exist that way if we execute a measurement on them under certain circumstances, but they actually can exist in superpositions where they are partly up and partly down, or partly something else, and they snap into place and take on what we call an eigenvalue and an allowed energy state when we execute a measurement on them. But before that, they're evolving smoothly according to the mathematics of the Schrodinger equation, which has been presented to you in all of its mathematical beauty a few times along the way here in our talks. That opens up interesting possibilities. Now, a little historical note. There was a truly great scientist, one of the giants of 20th century science was Richard Feynman. And he's responsible for a lot of things. I mean, he was a Nobel Prize winning physicist. He brilliant science educator. I have his books still, his physics books, and I make reference to them when I'm on a sticking point. He helped develop the theory of light and matter interactions called quantum electrodynamics, which was the first form of something we call quantum field theory that is actually what underlies quantum mechanics. In discussions I've had here with the Theosophical folks, I've talked a lot about quantum mechanics, but I haven't talked about the next thing that lurks behind it, which is called quantum field theory. I'll get there one of these days. I'll bring it up and start sketching some of the basic ideas. And it's a fusion, basically, of special relativity and quantum mechanics that allows for a next degree of explanatory power for physicists to bring to bear on the universe. QED, quantum electrodynamics, he actually has a popular book on that. If you were to type it in, just QED at Amazon, you would see, you could buy used copies of Richard Feynman's book explaining quantum electrodynamics for the public. And it's a fun read because he's actually a good writer. Well, he was involved towards the end of his life in some of the early attempts to carry out computations on quantum objects using classical computers. And he quickly ran into the terrible problem in that the combinatorics, the way in which quantum objects couple to each other and exchange phase information, if they are sufficiently entangled, explodes in numerical complexity very quickly. And you get to a place where, for example, let's see here. Well, if you think of quantum objects, essentially, if you capture them and you hold them in a device that is now going to use them in a computational fashion, quantum objects can be made to become qubits. Qubits meaning quantum bits. And quantum bits are different because they're quantum objects. They can exist in states of superposition between 0 and 1. They can be coupled to each other by virtue of phase correlation. Quantum phase is kind of a long discussion. I've briefly hit on it, but think about a spinning top. So a spinning top, spinning around like this. If we put it in a gravitational field, that spinning top, we could draw an axis, which would be the axis out the top of the top. So it's spinning around like this. That'll precess in a gravitational field. Okay, that precession is embedding phase information in it. What if we now think about the quantum level and think about a couple of quantum objects with spin, and let's say they're in a magnetic field. So there's some energetic discrimination between quantum objects with their spin axis aligned like this and precessing that way versus quantum objects with their spin axis aligned like that and precessing this way. Well, you can imagine that phase, which just means where are they relative to each other as they are precessing, is a fundamental component of the wave function we would write in order to describe that. And it explodes numerically in such a way that if you try to understand and simulate with a classical computer what's going on with quantum objects and how they interact, it gets intractable. So in order to, for example, track the information flows, which is another way of saying track the unitary evolution of the wave function, for even 10 qubits requires about 16,000 classical bits to even begin to capture part of the picture. So what Feynman came to realize after doing a number of experiments is that it's kind of hopeless for us to use classical computers in order to simulate and understand what quantum objects are doing. Once you have very many of them interacting with each other, it becomes intractable. The math goes off the charts, and you're quickly looking at problems that you're going to have to wait around the age of the universe before your computer can suss it all out. I do quantum calculations all the time on molecular systems that I care about. And what I can do is all about the levels of approximation that people can invent in order to simplify that problem. We come up with things like the density matrix, and we make approximations based on electron density in molecules and apply approximations. There's a field called density functional theory that I use all the time that doesn't even try to keep track of everything going on in the system. It's basically figuring out how to boil it down to the bare bones and make at least reasonably good guesses as to what's going on in molecular systems with just a couple hundred atoms. And so that's nowhere near material, right? It's the progress is impressive and beautiful. The fact that people come up with more and smarter approximations in order to extract more and more juice out of classical computers. But at a certain point, you lose the battle. And Feynman realized that if we're ever going to really simulate quantum objects and really understand what's going on with Mother Nature deep in the nitty-gritty, we're going to have to make computers out of quantum objects. This is the only way to do it. You're going to have to use quantum objects in order to do computations that allow you to understand how other quantum objects that you would represent are going to behave. There was a crucial paper in 1981 where he came to that realization. And this was around the time that people were coming to grips with something we might call quantum information theory. And how does information embody itself in Mother Nature, particularly in quantum mechanical systems? So there was a nice interplay there. Quantum chemistry, like what I do, was one of the main drivers of the progress in this area because it's so useful. And if you do it right, you can predict drug functions. You can predict spectra of molecules, their bond energies, thermodynamic properties. There's a very useful commercial value to all that. Another place where quantum information theory is very important is in cryptography. And this is where one of the early advances in quantum computing became noteworthy, and I'll explain it. So a lot of our cryptography by which we keep our bank accounts safe has to do with something called RSA encryption. And what that's referring to, the RS and A are the names of the three people who came up with it. The S might be for Shor, I'm not sure, because a fellow named Shor, S-H-O-R, was one of the key players in this area and had the first deep insights into how to use quantum computers in order, if we had them, we didn't really have it when Shor was figuring this out, but he was able to use what he knew about quantum mechanics in order to predict how quantum computers would impact the field of cryptography. So let me explain to you how RSA encryption works now. If you take two large prime numbers, like say with at least 5 or 6 digits each, and we have tables of prime numbers that we've discovered. We haven't discovered them all. You'll see articles appear in the science literature every time somebody figures out a new way to discover prime numbers. So prime number, you'll recall, is a number that can only be divided by itself and 1. In other words, you can't factorize it. Well, suppose you take two prime numbers that maybe they could even have like 100 digits each, some number of digits, and you multiply them. Now you get a big, long, scary looking number. Then you look at that, and that becomes a key to your encryption algorithm, is knowing what the two prime numbers were that give you this one big weird number. And I can't describe all the hoops and wherefores, but that ends up being the basis. Because if you just look at some number with, say, 200 digits in it and ask, what two prime numbers would result in this big, long, scary number? Well, a classical computer that uses just on-off of transistor currents can begin to approach that problem, but it has to do it brute force. It has to start going to all the prime numbers that it knows and seeing if they will divide into this thing and give you another prime number as a divisor. Well, that takes a long time for a classical computer to step through that, because you've got to try every single known prime number looking for the prime factors of this big, long 200-digit string that you're staring at and trying to crack if you're a hacker. Shor realized, however, that by using the magic of quantum objects in states of superposition, there's a way to pose this question to a quantum computer that has entangled qubits that will allow it to be factorized much faster. So this I think, basic realization happened somewhere in the mid-70s. And it's kind of scary, because what it means is that as quantum computers get bigger and better and more stable, there's a race. We don't know what embodiment that's going to be yet. As they get better, at a certain point, quantum computers will be able to pick apart arbitrarily large strings of digits looking for prime factors. I've got here a graph I pulled off the web that sort of, oh, I think I have a problem of sunlight. Let's see. So here's a graph I pulled off the web. If you look at what's being displayed here, I have on the y-axis number of mathematical operations, and along the x-axis is the number of digits in some big RSA encrypted key. Well, if you look at the number of operations required to factorize that, on the top line, which is a classical computer trying to do it, that scales as e to the cube root of the number of digits. And you can see that once you get up to 300, I didn't put it, so the tick marks along the x-axis are hundreds of digits. So it's got 100, 200, and then 300 digits. What you see is that if you go out to, the record, by the way, of a classical computer being able to factorize a quantum encryption key is 230 digits. So that's somewhere between the rightmost and second rightmost tick mark on the x-axis. Classical, that puts you up at somewhere around 10 to the 25th operations. 10 to the 25th mathematical operations, that's a lot of operations. You're going to be dead and gone long before the fastest supercomputer working classically would get to 10 to the 25th operations. Along the bottom curve is the Shor algorithm based on having a quantum computer at your disposal. In that case, so that funny little sign there that lays on its side, that means proportional to. So the Shor algorithm, which is a quantum algorithm that runs on a quantum computer, kind of goes up slowly and then it bends over and it stops moving so fast. And it's proportional to the cube of the number of digits, and it stays manageable. So instead of blowing up into 10 to the 25th or even 30th operations, it stays kind of civilized down there around 10 to the 5th, 10 to the 6th operations, which is not impossible with modern technology. Quantum computers don't necessarily run faster than classical computers, but what they're doing is exploring a much larger space using the combinatorics of qubits in order to arrive at answers faster. Using what we call quantum parallelism. So this kind of freaked out the encryption community. And right now, there are math departments all over the world and working with quantum computation experts, and they're trying to figure out how soon does the quantum computation apocalypse come, when hackers can figure out all of our encrypted information by factorizing these large numbers into primes. Because once they do that, they got your bank account or your nuclear secrets or whatever it is. And what's taking place is a complete redesign of cryptography. So this is a very alive field where math PhDs who are clued into this area get jobs. It's kind of an interesting moment because we're having to reinvent cryptography to make it quantum proof or quantum resistant, so that a bad guy with a quantum computer can't go out there and get all of our data. And it's an even bigger problem than it sounds like, because there's evidence to make us think that there are bad guys with ill intent who have been going out into the world on the internet and sucking up all the data they could get, even though they can't de-encrypt it yet. But there's big amounts of data out there in encrypted format that they'll suck it up, store it, and wait until they can buy a quantum computer in order to come back and de-encrypt it. It's an interesting cat and mouse, spy versus spy kind of game being played, but it's a very active game, and it's sort of interesting to keep a handle on it from a distance, which is what I've been doing. So I'm already at 50 minutes, and that's about as much as I feel like putting you through. I'm going to come back to this and expand it and try to sharpen some of these ideas, give you some better examples in the next lecture or two. And by the end of a couple of these periods of exposure, you're going to have a better sense of what quantum computers are and why they're so important. And I'll give you the preview that one of the reasons why they're so important is that I think they will be the key to possibly allowing us to create sentient AI. Right now, the various forms of AI we can create are, I believe, arguably not sentient. They are good simulators. They can fool most people into thinking they're sentient, but there's good reasons to believe they're not. Now, that could change. Somebody could always invent something or a new way to do clever things in a classical computer that allows it, modern current AI, to suddenly become self-aware. I wouldn't be betting on that myself. When we bring quantum computation into the mix, and quantum computers, by the way, always require a whole big bank and a lot of classical computational control. So you don't have quantum computers as a thing unto itself alone over here. It's going to be a module in a big rack full of controllers and processors and analyzers that are operating classically. Once those are invented, I think at least there would be some possibility of having sentient machines. Furthermore, one of the forms of embodiment of quantum computations involves qubits that are made with light rays rather than trapped ions or superconducting circuits or spinning electrons. Or there are many embodiments, but the one I'm most excited about is light. Using light to do the quantum magic, I think, is going to be what really defines a big change moment for humankind, because then we're going to be able to probably figure out how to make something pretty close to self-awareness into machines. And that's a speculation on my part, but it's based on a lot of reading and thinking. So thank you for being with me. One last announcement, which is that many of these talks now are being posted to the San Francisco Theosophical YouTube channel. And I know they are there. I have not been going back and looking at comments and questions up until now. But I'm going to change that. I'm going to start going and looking at the postings on YouTube of these informal talks I give. And if people have questions or comments or ideas, you want to talk about something there, I'll be checking in now and then, and I'll be happy to address your questions or suggestions for future topics or whatever that might be. That's something I'll be easing my way into here over the next weeks, and try to make that part of my paradigm. So nice to see you all, and I hope you have a lovely week ahead. Goodbye.